very exciting. And I would like to introduce John Russin. He's Vice Chancellor and also the G&HC Company Endowed Professor at the LSU Agricultural Center. His talk is entitled, A Regional Program for Production of Multiple Agricultural Feedstocks and Processing to Biofuels and Bio-Based Chemicals. With it, he happens to be the new project director of the project SUBI, a USDA Sustainable Bioenergy project led from LSU. And it focuses on energy cane and sorghum for biofuels and bioproducts. And so the talk will be 35, 40 minutes, and afterwards we'll take questions for Q&A. And let us introduce John, Dr. John here.
Thank you. Good afternoon. How many of you know anything about sugar cane production? Not sugar beet production, sugar cane production. All right, so we're going to cover a little bit of basic agriculture, but then spend most of the time. My cheater notes just disappeared from the screen there, boss.
Sorry, just got to change one thing.
I guess that's what happens when you are the inaugural talk, right? We're still getting the wrinkles out. I'll spend a little bit of time talking about some of the agricultural aspects of our project, the 5-year project, but I want to spend most of the time talking about some of the specific products that we can produce, which is why I'm here, to sort of build relationships, see where their partnerships might be available. I shouldn't say this, but I've got a little extra money in year 5 and 6, and I'm looking for ways to not spend it, invest it wisely. All right, right now I am waiting patiently.
And we have to hope that the wind doesn't pick up and us lose power during the inaugural talk. Just so you know, a lot of people have vacated the university already because when we had a windstorm 2 weeks ago, they lost power in some places, Spokane, for over a week.
Oh, my.
And we had to close down the university as well. It was quite intensive.
Well, I walked here from the hotel, and it was...
Oh, the new one?
Yes, it was brisk. There we go. Are we ready now, Carl?
All set for it, sir.
Okay. In Louisiana, we have a sugar industry. It's about 400,000 acres. We have 11 sugar mills, and they are basically biorefineries. They operate 3 to 4 months of the year, and we produce a product. It's called bagasse. Each of those 11 mills burns this bagasse. It's about 55% moisture. To generate steam to produce electricity. Now, what is bagasse? Bagasse is what's left after you squeeze the cane stalks and remove the juice. So basically, it's a waste product. It's largely burned on site, but even after it's burned for electricity, there are more than 650,000 tons each year, closer to 1 million tons in a very high tonnage year of cane. So we've got a lot of biomass with which we do very little to capture value. When we prepared our proposal for this 5-year grant, USDA told us that we were to work on 2 different species. One was called energy cane. The second is sweet sorghum. Now, energy cane is interesting because it's nothing but sugar cane given a fancy name. And it's called energy cane because for 175 years we've been breeding sugar cane in South Louisiana, and we select for low fiber and high sugar. Everything that didn't have low fiber and high sugar, we discarded as junk. Now that junk we have rebranded as energy cane because it has biomass potential. Sweet sorghum is something that has been grown in every grandmother and grandfather's backyard in the South for 100 years. They use it to make sorghum syrup, sorghum molasses. It's not grown commercially. So these were the 2 crops that were given to us by the USDA to focus on. We had 2 tasks, basically. Develop production systems, which is 100% agriculture. How do you grow this stuff? How do you harvest it? How do you transport it? What are the logistics of it? I'll talk about that briefly. And then secondly, what do we do with the products that come from this? And there are 2 product streams. One, of course, is the cellulose bagasse material, and the second is juices that we can concentrate to syrups, which have value chemically. Our goal was to develop a year-round feedstock supply. I mentioned to you in the first slide that Sugarcane is harvested only 3 to 4 months a year. The rest of the year, the plants sit idle. So our task was to identify and create a year-round supply of biomass. And so this is our target here on this slide. We've had many partners, industry partners are shown here, many university partners as well, and as I like to say, a cast of thousands of scientists in many different areas, student workers, postdocs, technicians, etc., helping us do this work. As I mentioned, energy cane is a tropical grass. It is a sugarcane hybrid, and therefore it is perennial. High fiber, low sugar, and we have worked on this in concert with the USDA Sugarcane Laboratory in deep South Louisiana in Houma. And we have been working to identify new varieties with molecular markers to identify lines that have cold tolerance. Remember, this is a tropical grass, which means you can't grow it much further north than Baton Rouge, which is pretty far south. So we wanted to extend its growth range north. We did that some. We've been able to get it to overwinter very nicely at about 32 degrees north latitude. What's the latitude here?
I don't know what's the
What's
latitude.
what's the latitude here in Pullman?
Well, it's not the Arctic
40,
Circle yet.
44, 46, 47. No one knows? No one knows?
Someone hurry up.
Okay, it's less than 50, but probably more than 45. So you're a fair bit further north than we, so these would never grow here. But over a couple of years so far, we have identified some lines that will do very nicely. This image you see here, and I'm trying to get, there it is, the mouse to work. This is energy cane. This is in year 5, and it still produces 8 to 10 dry tons per acre, which is about double of what you get out of the corn stalks in Iowa that they're using now to make ethanol. So it's a very high tonnage crop. Problem is that it doesn't grow very much in the United States. That green area is basically the limit to where you can produce this with any level of confidence. The black dot there is where we got it to survive at reasonably cold temperatures, that's soil temperatures of 1 to 2 degrees C. Anything colder than that, and it just dies. So that's about as far north as we can take this. So great tonnage potential, but very limited potential growth range. Sweet sorghum is different. It's an annual crop. It produces multiple potential feedstocks, juice, which we can make into syrup, seeds, which we can use to make starch, and of course stalks for biomass. It's annual, and depending upon the hybrid or variety you plant, matures in 90 to 150 days, and it's grown throughout the eastern United States wherever there's enough water. So from Minnesota down to Louisiana, you can find sweet sorghum capable of growing. Our industry partner here was Cirrus out of California, and we have actually developed production systems for this as well. It turns out that while energy cane requires basically no inputs after planting, sweet sorghum requires a little bit. It takes some nitrogen, and rather than use commercial nitrogen fertilizer, we've stepped up to look at whether we can use existing cover crops. You can see 2 here in front of you, crimson clover on your left, hairy vetch on your right. It turns out that both of those cover crops produce substantial amounts of nitrogen back into the soil, and that nitrogen has enough value to produce a very good crop of sweet sorghum, and it's much cheaper than replacement commercial chemical nitrogen fertilizer. So this helps to scratch our environmental itch as well. Sweet sorghum yield potential is far more widespread than energy cane. It doesn't produce as much tonnage per acre. Energy cane is 15 to 20 dry tons per acre, which is substantial. This is 10 to 15, sometimes lower, but you can grow it almost anywhere. So for a crop, it has far greater usability for growing to feed a biorefinery. A quick summary of these crops here. Energy cane can be harvested for 7 months, sweet sorghum 3 or 4. Inputs, none for energy cane, of course, after planting. A couple $100 an acre for sweet sorghum, which is very modest. Planting, annual versus perennial. They both can be grown on marginal lands. This is important. In our part of the country, you do not want to introduce a crop for fiber that competes with food. You don't want to enter the food versus fuel and fiber debate. So we stayed away from that. We looked only at marginal lands. We can produce these there. And the dry tons per acre are, again, very strong for both. So now we have a system where we've reached our goal. We have year-round feedstock supplies. Energy cane you can harvest for biomass from September through March. Sweet sorghum for biomass July through October. Bagasse, the waste, is available year-round. And syrups are available year-round. I haven't mentioned this, but we've done studies for long-term storage of energy cane and sweet sorghum syrups. We can store them for up to 6 to 8 months, similar to what you do with beet syrup in this part of the world. So we've reached that goal. We now have a year-round feedstock supply. Where will we produce these crops, and where might we site a biorefinery? That was one of our tasks as well. Rather than displace ag crops, we looked at marginal lands. These are lands of low fertility, high erodibility, that largely are not used for crop production now. There are almost 2.5 million acres in our part of the world. Our economists have gone in, and based on the density of that low marginal acreage and proximity to important utilities such as natural gas, electricity, rail, water, they have identified a series of sites where one could conceivably site a biorefinery. And you can see 5 in Louisiana, 4 in Arkansas, and 6 in Mississippi. So all you need now is about $100 million, and we can give you a site. Of course, you have to buy the site. But we can tell you where to put your plant. We can put you in a place where you can grow all the biomass that you need. We watched the movie Field of Dreams, where the quote came from, "If you build it, they will come," hoping that if we built this infrastructure information, the processing plants would come. So far, they have not yet arrived, but we're still optimistic. Our economists are working on this same model for the entire southern U.S., coming soon. Logistics for harvest and transport. One thing you don't want to do is introduce a new crop and say, oh, by the way, you've got to spend $3 million just for new equipment. So we examined all the different ways to harvest and transport this stuff. Turns out that the existing technology for harvesting sugarcane, which is right here, you cut the stalks green, you rip off the leaves, you put the pieces of stalk in here, or you can use this silage cutter here for either one of those crops. Existing technology, no modification required. It took us 4 years to figure that out, but it's nice to know that you can buy them commercially off the rack. A summary here, low input crops, so it won't cost you much to put them in the ground. And we have now published full-scale production guides for both of these brand new crops in our region. Just a very few comments on environmental impact. Soil carbon is important in our part of the world. And we've done a number of years of study looking at changes in the soil carbon pools under conventional and these biomass crops. Turns out that we are actually increasing soil carbon by growing energy cane or sweet sorghum versus conventional crops, which in our part of the world is corn, soybeans, cotton, wheat, rice, things like that. Wildlife and wildlife habitat also are being favorably impacted. The diversity and abundance of wildlife is actually substantially higher in these crops because they are incredibly dense. They're so dense that no weeds grow between the rows, and this creates a very wonderful environment for wildlife. We are a land-grant university, so we do a lot of extension work. Just a little bit of a snapshot here. Last spring, we devoted one of our quarterly issues of Louisiana Agriculture to this project. We do, of course, a number of field days like you all do, lots of education activities, summer youth camps, 4-H University, what we call Ag Magic, which is a statewide program to introduce agriculture to 3-year-olds up through 2nd grade. Lots of symposia, workshops, seminars, trade shows, etc. So we're doing our due diligence on the extension and education side. Now, I want to change gears and focus on the real reason why I'm here and talk about some of the different products that we can produce from these areas, these 2 different new crops. And I've broken it down into syrups, nanomaterials and biopolymers, biobutanol, and some specialty products. And I'm going to begin to tease these apart as best I can. Now, let me give you a caveat. I am not a chemical engineer. I am not a polymer chemist. I am not a mechanical engineer. So what I'm doing here is basically just summarizing information. I might be able to answer a few questions, but what I'm really able to do is connect you with the scientists back in Louisiana so that you can begin a conversation if you have interest to partner in any one of these areas. We can deconstruct biomass. We can take some of this bagasse and using some dilute ammonia pre-treatment and some specific enzymes, we can get a whole bunch of different products, starting with syrups and a bunch of specialty chemicals. Problem is they are very expensive. So while we can do this in a laboratory and some level of scale up, these are very high cost materials. So we can make all of these different things. You wouldn't want to have to pay for them compared to what they would cost from petroleum sources. These are all very expensive except for one, and that's called aconitic acid. It's an organic acid found in very high concentrations in our crop syrups, juices, especially in the molasses, and you'll see why this is important in a few more slides. We are working to convert our sugars, syrups, into feedstocks that could compete with corn syrup. And so looking there on your left, you see one of our scientists standing with energy cane. It can get taller than that in one season. We grind it, we produce the syrups, and when you look on the right, you see very dark syrups, almost look like molasses. That's traditionally what cane syrup looks like. It's from this that you evaporate and recover raw sugar. Some stores sell it as turbinado sugar, but it's raw sugar that's then refined back into white sugar. Incidentally, if you buy brown sugar, that's not raw sugar. That's white sugar with a little bit of molasses added back in. So when you look at the chemical composition of these syrups, energy cane and sweet sorghum are fairly similar. Fermentable sugars are a little higher in the energy cane. Lots of mineral ash, which is a problem. Sugarcane molasses is there as well. Very high ash level. And our target is refined dextrose from corn. Greater than 99% fermentable sugars and less than 0.05% mineral ash. And so if we want to compete with this market, that's what we had to reach. So we began to deconstruct some of these syrups, and you see that a typical syrup has roughly 70 to 75% dissolved solids. Of that, this sample shows 8.4% ash, and when you break that apart, this is your composition. All of these minerals here are death to catalyst beds that our industry partners are using to make their value products. So we had to get these out. So we worked for several years, starting with the raw syrup on your left, using microfiltration, electrodialysis, ion exchange. We're now moving toward simulated moving bed chromatography to do larger volumes, and our goal is to get a product that specs the same as corn syrup. And what you see on the right, except for a little bit of color, specs exactly the same as corn syrup. Here are the numbers right here. So looking at fermentable sugars where we started, where we wound up, we are now more than 99% fermentable sugars, actually substantially lower ash level. Got a little bit of color that we got to work out through chromatography, but we have a product that specs the same as sugar syrups from corn. And we've got a company in Louisiana called Miriant that is interested to work with us to sample some of these syrups in large quantities, because they have a process that takes corn sugars and through bacterial fermentation produces biosuccinic acid. So that's where we're headed with this. Our industry partner in this initiative is Virant. It's a biotech and biomass company out of Madison, Wisconsin. This is a very concise snapshot of their conversion platforms. Our technologies fit in here, where you see the LSU symbol. We feed them our conventional sugars. We can also deconstruct our biomass to get sugars. Again, a much more expensive pathway. But we wind up with, there we go, two product streams that we feed into. One is their aromatics and gasoline stream that gives paraxylene, which is critical because that's fed into the polymer market to make green plastic drinking bottles. And the bottom line, the distillate goes into jet fuels as well. And so we've got syrups now that are pure enough to work into these streams. And we actually sent some syrup up, and Virant was able to produce 100% renewable bottles using our sugars. I asked for a case of these. They laughed at me. And they said, starting at $250,000 just to scale up enough to get a couple of cases. And then I'd have to pay a separate contracting company to polymerize and produce the bottles. So they said roughly $400,000 for a case of Coke bottles, which I wanted to take to my legislature next year to show them what could be done. I'm changing my mind right now. Those are really expensive bottles. But anyway, I can show a picture, and it's almost worth the same. Shifting gears to another product, cellulose nanomaterials. We can deconstruct our stalks as well and get cellulose nanofibers, nanocrystals. We have some scientists who are doing some early work in energy storage devices. I heard the word battery mentioned earlier by someone, so this might be a possible way we can link up some scientists. We're working on cellulose hydrogels. This is the material that they put in disposable baby diapers. We actually have some products that we've developed from that that look pretty good. And we also can put these cellulose nanomaterials into a product maybe not known much around Washington, but very well known in Louisiana, drilling fluids. Very large market globally. We already have some technology into this market. Halliburton licenses it, and they may be interested to talk to us about this as well. So, another high-value product. Moving into biopolymers. Corn, of course, is the sector leader. Corn plastic is in just about everything, projected to grow substantially over the next 5 years, especially with regard to biodegradable plastics. We can make plastics, and it's long been known that we can do that, by going into these stalks and getting out the aconitic acid. I mentioned that earlier. So we can make some plastics out of aconitic acid, adding some other cross-linking materials to it. And these are just a few of the samples that some of the polymer chemists have produced. They just started on this project a few months ago. I told them I wanted an LSU Tiger football helmet, so I can take around. All I got was LSU in three different colors. And the picture on the right is a different composition. It's more of a transparent plastic. So they're working on a number of different potential composites by adding different things to the aconitic acid and getting different mechanical, thermal, optical properties. And some of them have actually been shown to be biodegradable. So kind of exciting. Lots of different potential applications for this. Again, I am not a polymer chemist, but I know there are lots of them in this building, perhaps in this room. Let's talk. Biomedical applications. We've hooked up with some biomedical scientists, and we've looked into the world of polymers for human cell scaffolding. Looking first at bone grafts. It's a very large market in the United States, and we have worked to produce, using our polymers from these crops, we can get biodegradable bone scaffoldings that we can use to grow bone cells to help with broken bones, hip replacements, things such as that. And we can vary the pore size based on the different composition of the composite, ready for animal testing. The same with skin scaffolding. We can start out with aconitic acid and glycerol, get more porous product if we add a little cinnamic acid in there, and we can produce skin cells. And this simple slide here shows that after 2 weeks, DNA, animal cell, human cell growth on these scaffolds is just about the same as it is on the check. So basically the human cells are surviving, they're growing very nicely, and we think that these products are ready for animal testing and could have a potentially very great biomedical product market. Another area we're working on has been biobutanol. You all know about this, fairly large market, both for specialty chemicals and potentially for liquid transportation fuels. We have a bacterium that we're working with in concert with a partner company, Clostridium, produces butanol, isopropanol, and ethanol from our syrup feedstocks. And we started out by doing very simple batch fermentation. We're moving on to continuous fermentation, and we're up to about 10 grams per liter per hour for butanol production, which is pretty impressive. And the next question is, now that we produce it, even at 10 grams per liter, it's still a very low concentration in a very large water environment, waste stream. And so we've got to pull it out, and that's been much more of a challenge because this stuff azeotropes, has a high boiling point. And so we're looking at a number of different strategies to actually separate the biobutanol from this waste stream, reverse osmosis, adsorption, perstraction. And we're using a number of different solvents to partition against it. Right now the favorite one is biodiesel, but even then it's not very good. Its partition coefficient against butanol is only 1.13, so we got a ways to go here, but we're getting closer every day. Last few slides deal with high value products. I had a sandwich and a beer with a polymer chemist one day and said, you know, I can do some things with some of this stuff. And after about 2 weeks, he came back with a number of different products. This happens to be a wood filler product made from our bagasse material and a bunch of adhesives that are made from our syrups. And it's polymerizable, which means you put it in your hole in your wood, you put a heat gun on it, it polymerizes in 10 seconds. It's hard, it's dry, it's sandable, it's drillable, it's paintable. And this stuff, if you bought wood putty at Home Depot or Lowe's, you know you pay several dollars for a very, very small amount. So this and a number of other products we're looking at as little niche high-value products. And with that, how much time did I have? Okay. I have a little bit before 4, so that's about 25, 30 minutes. Any questions? Yes, sir.
How did the body energy compare when your corn syrup substitute? You went through the purification and filtration. You got something that would work.
Yes.
But did you have to put so much energy in it that it could keep it up?
We're working on that right now to get the final answer. Based on what we know about how they purify corn syrup, it's a multiple step process as well. If we had to do it the way we did it, it probably would not be cost competitive. But before I was here, I was down in Idaho at Amalgamated Sugar Research, and we're looking at using one of their chromatography systems to de-ash very large volumes of this very quickly. So we think we can get it to a cost competitive, energy competitive state. Yes, ma'am.
So if you don't mind getting back to more basics, and I'm not in this field at all, so what's the difference between a juice, a syrup, and a molasses? And the big question is, from your crops, are any of these going to be used for food?
Yes, yes.
Okay,
Okay,
so-
let me go back to some basic sugar information.
Okay, good.
When sugar cane is grown,
Yeah.
I mentioned we have about 400,000 acres. We can't produce any more sugar cane because we're on a quota. Because all of our sugar feeds into U.S. consumer table sugar. So we're allowed so many tons per year and no more than that.
Oh,
And so when you grow the cane, you grind it and you get a juice. It's a very dilute juice. Think in terms of very dilute orange juice. Well, you have to concentrate that before you can begin to crystallize the sugar. And so as you put that into multiple effect evaporators, triple, quadruple, quintuple effect evaporators, and you take that down from 6 to 8 bricks all the way down to 60 to 70 bricks, it basically greatly enhances sugar concentration by evaporating off the water. That then is called a syrup. That's transportable, it's stable, it's storable. Molasses is what's left over from the sugar process when they get every gram of sugar they can from the juices and the syrups. What's left is molasses. It's a liquid. It still has about 50% sugar, but they can't remove it with the existing technologies given the price point for sugar. And it happens to be very high in mineral ash, so if you're a fan of health foods, that's why blackstrap molasses is so good for you, because it's very, very rich in minerals. It's basically because it's full of ash that we don't have the money to separate, so that goes into the cattle feed market. So hence a simple explanation for juices, syrups, and really a captured value waste product, which is molasses.
So if you're restricted from making more sugar, why aren't you growing sugar cane for these other products, or is that just because of the food versus energy argument?
Well, there is that debate, but it's an interesting question. A lot of sugar politics run deep in this country, so I will dance carefully.
Okay.
We have been approached by several companies who want to tap into our sugar stream for industrial purposes. Okay, there's no conversation there. These folks have been producing table sugar for 250 years. There's no conversation. They are interested to expand the sugar acreage. And so it's entirely possible that we could double, even triple potentially our sugarcane acreage, if we had a non-food market for our sugar. Energy cane was selected, sweet sorghum was selected, because they are not tariff-protected crops in the United States. We could grow those to our heart's content. Energy cane has, probably 80% the sugar of commercial sugar cane. Sweet sorghum actually has higher levels of sugar. So if you're going to introduce a new crop, which is politically far more attractive than trying to displace table sugar, those seemed like reasonable alternatives to the USDA. Realistically, probably the shortest path to commercial success would be to increase the existing sugarcane acreage. Our mills, our 11 mills, some of them have capacity to expand processing. So they could probably harvest more. Our constraint there is that we harvest sugarcane beginning the end of September, and we usually finish by Christmas. If we go much beyond that, there's a risk of a very horrible event occurring called the freeze. And when a freeze occurs in South Louisiana, not only do I have to cover my citrus, but it cracks the stalks on the cane. And when that happens, it allows microbes to enter the stalks and the sugar level goes down. So our industry is designed to focus on a very narrow grinding season. So if we can, for example, introduce sweet sorghum, where you can start grinding several months earlier, you can extend the profitability period for these mills and not impinge upon commercial sugar.
So can the mills be used for these different crops
Yes.
at different times?
There are a few modifications you need to make to a mill to accommodate energy cane, which has a more dense stalk, higher level of fiber. Sugar cane has a less dense stalk. So that requires adjusting of the mill settings to allow the spacing to be modified a little bit to accommodate those different speed stocks. But in our pilot mill, we've done that. It can be done.
And there's no issue of the mill doing energy cane and then doing sugar cane, which is a food crop. There's no issue.
No. We are allowed a tonnage quota for table sugar. And once that quota is reached, you can do whatever you want to with the rest, but you just can't sell it for food. Yes, yes, sir.
So when you did your site analysis to determine where you were going to put your refineries at, were you looking at that being in addition to an existing sugar refinery, or is that?
No. The existing sugar refineries in Louisiana are very far south. Let me see if I can. Please bear with me. I want to go back about 60 slides. I know this is really unprofessional, but my tech guy is not here to help me out, so I'm just kind of winging this.
Oh, back there, yeah.
Okay. Start with this picture. The furthest north sugar mill is right about here. Can you see that cursor wiggling?
Yeah.
That's it. All the others are in the sugar belt, right in here. It's a pretty small area of Louisiana where the soils are right and there's sufficient moisture. So they're all right about in here. The sites that we identified are outside largely this area. Where's my cursor? Okay, the furthest north mill is maybe right here. We could accommodate some sites here. That's outside, that's further west of the existing sugar belt, and all of these others in North Louisiana, Arkansas, and Mississippi are much further north than the belt. We can't produce energy cane that far north, and we can produce sweet sorghum that far north.
So, but your refinery concept that you're basing that dot on, was that based upon just building a fresh plant?
That would be if you were starting with a greenfield plane. Okay, where would you put it so that you had sufficient access to the acreage you need to produce the tonnage that you need? And we worked out how many tons per day that a plant would need if they're running for 9 months of the year, and how many tons per acre in different parts of the range. So these reflect the amount of acres you would need for a single plant to run 9 months of the year. And so there are, in North Louisiana, there are 2 side by side. There are enough marginal land there. We also overlaid that against existing utilities that we knew to be present, water, natural gas, what have you. And those sites popped up as the places to look first if someone had an interest to construct one of these biorefineries from scratch. But as I said, the easiest thing would be just to take one of the existing 11 biorefineries, sugar mills, and expand on what they do by extending the season or adding new crops or a combination of both. Yes, sir.
In my youth, I grew some sweet sorghum in Indiana, and it also has the advantage of fitting in nicely with their normal crop rotations of corn and soybean and their wheat. But one problem I noticed was this stuff grew to about 4 meters and really just jumped out of the ground. Beautiful, and then it lodged.
Yes.
And then it formed this mat, and it started shooting roots out of each node.
Yeah, that happens.
So how do you, I don't, first of all, I don't know if sugar cane does that, maybe you're used to this, but when you harvest it, how do you get in and harvest that without getting all sorts
Okay.
of dirt?
How many years ago did you grow that sweet sorghum and have it lodge and grow roots at the nodes?
Don't tell them.
It was in 1981.
Okay, so some time ago. One of the reasons that we worked with Cirrus out of California, this is our sweet sorghum technology partner, is they're developing new varieties and new hybrids of this. Lodging is still a challenge, especially in the hurricane belt where we are. Almost nothing stands up, including oak trees, if the storm is big enough. But we have a lot more standability. And we've also stepped in, and if you're familiar with that part of Indiana, they grow something called Sudex. Sudan grass sorghum hybrids. They routinely lay on their sides, and these can be harvested using traditional forage harvesters. They can pick that stuff up. With sugarcane, energy cane, when a crop goes down, generally it will right itself to some degree unless we have a very late season hurricane where it does not have enough time. And then you have to pick it up off the ground, in which case your ash level goes from 8% to 15 or 20%.
So with the cane, do you still spray it with an defoliant and then burn that? Or
No, we do not defoliate the cane. We do spray dilute concentrations of Roundup to what we call ripen the cane, to enhance senescence a little bit. You can sometimes get a bump in sugar tonnage that way. And then we harvest the stalks green. The leaves are removed during the harvesting process, blown out on the field as trash. The stalks are chopped up into billets, we call them, maybe 2 feet long. Those are loaded in wagons and hauled to the local mill, and the mill is never very far because you can't let more than 24 to 36 hours go between harvest and process because the sugar level starts to crash. Yes, sir.
Yeah, you mentioned that you use cellulosic nanofiber fluid for the drilling
Yes.
purposes. What's the function? Is it just to increase the viscosity? Or what
Yes, to increase the viscosity. If you are familiar with drilling fluids, in our part of the world we call them drilling muds. And they're called muds because they're put in there with the drill to basically seal the holes in the rock. So when you hit a reservoir of oil or gas, most of it comes to the top and doesn't ooze out through the sides. Several years ago, one of our scientists in materials area developed a product where he used some plastics mixed with cellulose from wood. And actually, that's a product that we now sell called Tiger Bullets. And it's added to drilling fluids to increase the viscosity and plug the holes. And we have products that will work at high pressure and low pressure. So this was an easy product path to begin to test some of these. Turns out that they work very well, at least in initial testing. But if you have interest beyond that, send me an email or see me afterwards. I'll give you my card. I can connect you with those material scientists. Yes, ma'am.
So I work more in the inorganic world, like with concrete, and I was interested in your ash. So is the ash a waste product that you're taking out of this as your...
At this point, yes.
And I noticed that it's high in content with chloride, potassium chloride, not so much the calciums or magnesium. So I'm interested in whether it has any cementitious properties at all. the
Okay,
ash has.
let me address the chloride.
Okay.
During the sugar the process of grinding to get juice that you concentrate to make syrups, you have to lime that. So the calcium chloride, most of the calcium and the chloride come in that way. So that's added. And then when it's removed, at this point, it's just a waste. It could conceivably go into fertilizers or what have you, but no one's tapped into that.
So you don't know if it has any cementitious capabilities?
Not at this point. Recall that in traditional or commercial sugar production, all of those minerals wind up in the molasses.
Okay.
And the molasses is then sold as a product into the animal feed market.
Correct.
With our system, we need to remove that ash. Now, corn syrup is a lot cleaner. It doesn't have very much in the way of ash contaminations. Ours does. Tell you what I can do, if we're working with our colleagues over in Idaho, I'm trying to send them 300 gallons of syrup from this grinding season to put through their chromatography beds. If it's possible, we might be able to recover some of that mineral ash and perhaps make it available to you if you want to play with it.
Yeah, and I would, and everyone here knows that I work on pervious concrete, and our big issue here is the fact that we put on chloride-based de-icers, and it basically dissolves the cementitious capabilities of it. And if there's an alternative that's more resistant to it, then that would be a great alternative for applications in the cold.
I never thought about that.
They all know I always talk about pervious concrete, so. Any other questions?
Any other questions? Hearing none, thank you for your attention and your questions.
So you talk even faster than I do.
Well,
I could talk faster.
I could have stretched it to 50 minutes, but I decided to just cut it to closer to 30.
So they make fun of me.
I'm a graduate of the University of Maryland.
Oh, okay, so you know what it's like.
Yeah.
But I actually talk. Like never really heard me talk.